It's a great, great honor for me to be here, particularly because Brooklyn, actually, is where my dad grew up, on East 56th Street and Linden Boulevard. Yay! And in the 60s, he went to Sweden, fell in love with this tall blonde woman, Mommy. The rest is history. They're still there, but I'm back. So, thank you so much. What an awesome energy you have here. And tonight, I want to encourage you all to think big. Because my main theme is that we humans have again and again and again underestimated both the size of our cosmos and also underestimated the power of our human minds to understand it. So to see what I mean by the first part, underestimating the vastness of things, let's first remind ourselves of what we humans have managed to figure out so far about our place in space. Let's begin at the Himalayas here. Let's just for 2 minutes shut the lights off completely, and then we'll get them back on again as we head off into space. The ancients, of course, were quite blown away when Eratosthenes first figured out the vast size of this ball that we live on, planet Earth, that is actually 40,000 kilometers around. And what's so impressive about this is he managed to do it without even traveling a large fraction of the distance, just by letting his mind fly and using some very clever observations of the sun and angles that I talk about in the book. And this sort of human ingenuity, before long, enabled us to actually send things up off the ground. We see here orbits of the near-Earth satellites that help us communicate with each other now. This beautiful simulation here was made by the American Museum of Natural History over in Manhattan, and I love it because everything is totally accurate and nerdy and to scale. So it's not just flashy eye candy, okay? Now, these satellites, of course, are very, very far away. But again and again and again, we humans have realized that everything we thought existed was just a small part of a grander structure. Coming into focus now is the moon's orbit around Earth. Notice you couldn't even see Earth anymore because this is the scale. Now we see the planetary orbits, but where are the planets like they used to be in our storybooks? Well, they're so small we can't see them. It's the scale. That's how vast our solar system is, okay? When you see the sun, you see the way it was 8 minutes ago, because that's how long it takes for light to get here. That's pretty far, but it takes hours for light to get to us from the outer solar system. And this was kind of our universe in my grandma's time when she was a kid. The solar system, some stars, and now, of course, we know that this too is just a small part of a much grander structure, the Milky Way galaxy, which is gradually coming into view here. And I want you to raise your hand if you know anybody who was born before 1925. When those people grew up, they didn't know that we lived in a galaxy, that there were other galaxies. That's how recently this mind expansion has happened. And now that galaxy with its hundreds of billions of stars is just one galaxy among billions and billions. You can see the vastness here, which in turn form larger objects, groups, clusters, superclusters, gigantic filaments. The Sloan Great Wall that I and my colleagues on the Sloan Digital Sky Survey spotted is a billion light years from side to side. And yet this still is part of something even grander, what we call our universe. Maya, can you start inflating our universe for the benefit of the rest of us? You see coming into view now is the spherical region of space from which light has had time to reach us so far during the 13.8 billion years since our Big Bang. This is what we affectionately call our universe, our home. This is all we can see. Even if we build arbitrarily good telescopes, because light from farther away here, if there is more space, which there probably is, simply hasn't had time to get here yet. To see stuff out here, you would have to wait billions of years more for the light to reach Earth here in the center. Now, all of this zooming out, even though it's kind of mind expanding, it's pretty intuitive. There's just more and more stuff, right? But what on earth is this yellow and green and blue weirdness on the surface of this ball? I owe you an explanation. And I also owe you an explanation for this hissing sound as my wife Maya inflates our universe for us here. To understand what this is, thank you, Maya, for the universe. This is our universe, the region of space that light has reached us from so far during the past 13.8 billion years. And if you promise to be gentle and loving and tender with it, I will let you play with it, as long as you give it back to Maya afterwards. To understand what this is, it's not enough for us to explore our place in space. We also have to explore our place in time. Fortunately, it's surprisingly easy to learn about our place in time in cosmology because the sky is like a time machine. We talked about how we see the sun not the way it is now, but the way it was 8 minutes ago. And if you see some stars on the way out, and if they're not just optical hallucinations induced by the Fibonacci cocktail, you know, you're seeing those stars the way they were maybe a few hundred years ago. And someone out there wouldn't see the Secret Science Club, but they might see Benjamin Franklin doing his stuff, okay? Or a Revolutionary War battle a few hundred years ago here. So when we look at this, we're actually seeing some galaxies the way they were billions and billions of years ago. And from that we can learn what our universe was like, both more recently and in the distant past. What have we learned about the history of our universe? I talk about this in great length in the book, of course, but let me try to summarize some of the highlights in a single slide here. What we basically learn is very surprising when we look out into the sky. And to just appreciate just how surprising it is, I want you to each imagine for a moment that you've had enough Fibonacci cocktails to imagine that you are a galaxy. Each one of you, okay? What do I see when I look out at you galaxies sitting here? Well, I see something really weird. In the front row, I notice everybody is in their 90s with canes and walkers, but you're full of energy. It's awesome. It's great. And behind you, I see a lot of people in their 60s and then 50s. And then I see a whole row of teenagers sitting in a semicircle around here. Behind you, I see some middle schoolers, and then some kindergartners, and then some toddlers. And then in the second last row, I see only infants. Only infants. And the very last row is completely empty. And as if that weren't weird enough, the back wall of this room is glowing with a strange glow of microwaves. What is going on? Why would you guys have conspired coming in to organize yourself by age? And what's that glow? And as if this weren't strange enough, there's another thing. You're all blushing. Those of you in the front row are just a little bit pink in the face, but those of you near the back are like tomato red, ketchup red. That's what I see when I look through a telescope into our universe. What's going on? Well, first of all, we already talked about how the farther away you look into space, the farther into the past you're gazing. You're seeing things which happened longer ago, right? So when we look into space, we see nearby, we see mature galaxies that have had time to grow up and get big. Farther away, we see just baby galaxies, because we're seeing the way the galaxies were so many billions of years ago that they hadn't had time to mature and become big ones. This is what it looks like. And when we look really far away, the back row of the room, we see no galaxies at all. Why? Because we're looking so far back in time that we're seeing an epoch before the galaxies had been born. What is there here? What is all this black stuff in the space images? When I was a kid, I thought it was vacuum. Now I know better. It's simply gas, hydrogen gas mostly, which is transparent, like the air in this room, so you just can't see it. It looks black. This is a gas that was later assembled into all these amazing galaxies that we have now. So that's why you were ordered by age. But why were you blushing? What was so embarrassing about this? Well, if you go down to the highway, and it's not rush hour like when we came, you hear cars go, ew, ew. You hear the pitch drop towards a lower frequency as the car recedes from you. The frequency of the sound gets lower when things move away. It does not go, ew. goes, right? It's exactly the same with light. The frequency of light from something moving away from you moves to a lower frequency. We call it the Doppler effect. So things look more red, because red has a lower frequency. We call it redshift. Galaxies would look redshifted if they're moving away from us. So this means that all of you guys are moving away from me. And if you're twice as far away, you can calculate that you're actually going twice as fast away from you. That's why the ones in the back look so tomato red. This is what we mean when we say that our universe is expanding. Everything is flying away from everything. And as I talk about in the book, you can work out from this that there actually seems to have been a time when everything was pretty much in the same place, on top of itself. So some great calamity seems to have happened in the past, and you can figure out how long ago it was. It was about 13.8 billion years ago. We have no idea exactly what happened. We have a fancy name for it, though. We call it our Big Bang. But we have a very good idea for what happened during the 13.8 billion years since then, because we can actually see much of this epoch with our best telescopes. And there's one more thing which sheds further light on this. I mentioned the back wall of the room was glowing. Why would it do that? Well, if everything is expanding, so is the gas. If you take a gas and you expand it, it gets colder. That's how air conditioners work, right? And your refrigerators. So as we head backward in time, all this gas would have gotten hotter and hotter and hotter. What happens to a gas when you heat it up more and more? It turns into a plasma, exactly. And a plasma is not transparent, it's opaque. So what it actually looks like to us is as if beyond all the galaxies we look at, there's just this plasma screen. Very, very weird. And since it's caused by just looking far back in time, it'll look the same in whatever direction you peer. So it looks to us actually like we're surrounded by a plasma sphere in all directions. Who is the keeper of our plasma sphere right now? Our universe. Has it left us? All right. What you see on the surface of that beach ball are photographs of this plasma sphere taken with exquisitely sensitive cameras on the Wilkinson microwave anisotropy probe, one of the most successful NASA missions of all time. Took these awesome photos of what our universe looked like when it was only 400,000 years old, and it revolutionized our understanding of cosmology, and for a cost of about 40 cents per American. So it's quite astonishing. Some people wondered if maybe this was too good to be true, if they had messed up the data analysis, it was a little bit wrong. Well, last March, we got an even better photo, not 3 megapixels, 50 megapixels from an even better satellite. And look, beautiful confirmation. All the spot and the patterns there are the same, except the image is now even sharper. So it's really quite remarkable. Now, in summary, we've underestimated not just the size of things, but how much we could figure out. When I first started grad school, we would argue about whether our universe was 10 billion years old or 20 billion years old. Now, as a result of this wonderful data, we argue about whether it's 13.7 billion years old or 13.8 billion years old. So that's progress, but let's not get too arrogant here. Let's remind ourselves of how great mysteries still remain. For instance, one thing which has become clear is that we have no clue what 95% of our universe is made out of. The atoms that make up us and the Fibonacci drinks and everything else here make up only 5% of our universe. And you've all heard about dark matter and dark energy making up most of the rest, which are really little more than fancy words for our ignorance at this point. And I talk more about it in the book, what we do know about it. But clearly we would like to know. In fact, to figure out what the dark energy is basically equivalent to figure out what our universe is going to do in the future, which is obviously a fascinating question in its own right. So we would love to get better data. We'd also like to know what really happened early on with this Big Bang and the particulars of it and what caused it. So are there more data we can get? Yes, there are. Let me show you how little we've accomplished. If we just peel off the outside of this universe, this ball, please don't do that with the one you're passing around. You see, all those galaxies I flew you around in initially make up just this tiny region in the middle here, near Earth. Less than 1% of our universe. And then these baby pictures come just from the inside surface of here, shown in yellow. Again, less than 1% of the volume. So the vast majority here is just uncharted territory. We would love to map all of that stuff. That would give us amazing clues about what dark matter is, what dark energy is, and details of our Big Bang, and so on. Fortunately, there's a really cool idea for how we can do this. Because even though we can't see galaxies here because they haven't formed, they're so far away, the gas which is here, the hydrogen, can actually be seen. Because hydrogen turns out to give off radio waves, 21 centimeter long radio waves. So there's actually a whole bunch of different groups across the planet now trying to build awesome radio telescopes to make three-dimensional maps of the rest of our universe. And I want to share with you just how much fun we've been having at MIT developing new technology for this kind of experiment. I'll show you how to build a radio telescope in just 2 minutes to see how easy it is. Very easy and quick. Thank you. It's, I just feel so fortunate to get to be a scientist and spend most of my time thinking about these questions, which are just so cool. I would happily think about them anyway as a hobby, and that I can actually call it a job is downright scandalous. And for those of you who have kids, or are kids, or have an inner child, I want to emphasize that it's fun not only because it's just such an exciting intellectual quest to think about this stuff, but also because you get to hang out with these amazingly friendly and idealistic people, all of whom could make more money if they chose to not go into academia, which means they're doing it for love, for passion, because they are obsessed and fascinated by this, which is the best reason to do anything. So there's a pure joy to get to work with people like this. And now, in summary, we've figured out an enormous amount of stuff, we humans, about our place in space and time, about our universe. And I've convinced you, I hope, that there are vast mysteries remaining as well, and that there are all these fresh and exciting ideas for how we can learn more. In the years ahead, I talk a lot about that in the book too. And that closes the loop and brings us back to these two themes that I opened with, right? We need to think big, because we kept underestimating both how vast our cosmos was, but also the power of our human minds to understand it. And that raises another question. Why is it that we humans have been able to figure out so much? Our ancestors who walked the earth 50,000 years ago probably had just as big brains as us, were about as smart as us, and they probably spent even more time than we do gazing at the stars because they didn't have television. And they wondered, what are these sparkling dots doing up there? They came up with creative and wonderful myths. I think at the same time many of them felt a little bit melancholy, knowing in their hearts that they would never be able to figure it out, that it was just not possible for humans. We couldn't go there, we couldn't touch them, how could we ever know? And yet now, it turned out we had the power within us all along. We've figured out all these things, ultimately not with rocket power, but with the power of our minds, by letting our minds fly, right? And why is it, more specifically, that we've been able to do this? It's not only because of the awesomeness of our human minds, of our consciousness. It's also because nature has provided us with all these hidden patterns. There's an elegant simplicity and beauty in nature revealed by mathematical patterns and shapes, which our minds have been able to figure out. And why is that? This idea that there's something very mathematical about our world is an old one. Already in ancient Greece, Pythagoras said that numbers rule the universe, and by the time the Renaissance came around, Galileo was so impressed by all these mathematical regularities that he and others had found that he wrote that our universe is a book, a grand book written in the language of mathematics. But where is all this math that they're talking about? We heard about how we were supposed to walk down the street and look for squares and circles and stuff, but those square windows were built by humans, right? And numbers, do we see any numbers here? Yeah, I see a number. It says 1623, but this was written by a human. And so this doesn't tell us anything fundamental about nature, right? So where is all this math around us that people talk about so much? Well, as you can see from Galileo's longer quote here, to him, math is not just a bag of tricks for manipulating numbers or a sadistic form of torture invented by school teachers to make us feel bad about ourselves. It's also about patterns and shapes. And if you throw something up in the air, it makes a beautiful shape. And Galileo noticed that whatever you throw, it makes the same shape. What do we call this shape? A parabola. And it has a very simple mathematical equation. Y equals x squared, if you draw it like this. Moreover, by looking into the heavens, we discovered again there's a certain kind of shape that everything orbits in, called the ellipse. It too has a simple equation. And moreover, for those of you who are hardcore math nerds, if you look at the tip of an ellipse, it's very well approximated by a parabola. And in fact, if you calculate really carefully even how a baseball flies, without air resistance, it's actually not a parabola, it's actually a little piece of an ellipse. So it's all unified into this very simple mathematical shape. Math everywhere. We professors have a lot of bad habits. One of them is we love giving just unannounced pop quizzes. And I'm sorry, I just can't help myself. So you're going to have to suffer through one too. Here's the quiz, okay? 3 great discoveries. The discovery of the planet Neptune, discovery of the radio wave, discovery of the Higgs boson. Which tool triggered the discovery of these 3 things? Don't be shy. I hear telescope. Anything else? Looking for an answer that works for all 3 of them. Human mind? Mathematics. That is the correct answer. Don't worry, this particular quiz is not going to be graded, but there might be another one on the way out. We'll see. If you want to be really finicky, you could say the tool was the pencil, because they were all predicted through mathematics. Astronomers noticed that the planet Uranus wasn't moving quite the way Newton's equations predicted. So the French astronomer Leverrier calculated, and then he wrote a letter to a German astronomer named Gall in Berlin and said that if you point your telescope to such and such a place in the sky at such and such a time, I predict that you will there find another planet. When Gall got this letter, what would you have thought? Maybe that the guy had one Fibonacci cocktail too many, or that he was cuckoo for Cocoa Puffs or something, but you would be very curious too, wouldn't you? And he was, so he pointed his telescope at that place. Boom! There was the planet Neptune, predicted through mathematics. A few decades later, James Clerk Maxwell tries to unify everything known about electricity and magnetism, and does so with these beautiful equations that are called Maxwell's equations, which I'm teaching a course about at MIT starting in a couple of weeks, and students even like to have them on their t-shirts sometimes. And he predicted, based on this, just through math, that if you build a certain kind of device, you should be able to use it to transmit a new kind of wave, a radio wave that travels at the speed of light. It can go through empty space, it can go through walls, and be used for sending messages. The machine was built, boom, it worked, and raise your hand if you have a cell phone in your pocket. The power of math. Then most recently, and most famously of all, of course, Peter Higgs took the most advanced mathematical description we had at the time, the standard model of particle physics, calculated and predicted that if we humans build the most advanced machine ever built by science in Geneva, and we crash particles together in a certain way near the speed of light, we will there produce a new kind of particle, the Higgs particle. The machine was built, boom, there it was. You know what happened? He won a free trip to my hometown. So, why is mathematics so powerful? And as if those three examples weren't enough, we have now, with just a small number of equations, managed to summarize this vast body of knowledge about the physical world. And my wife Maya here was actually kind enough to let me put this up in our living room. I'm a little bit embarrassed, but she's a very forgiving wife. We still haven't figured out quite how to get these equations, Einstein's general relativity, to get along with this equation, the Schrödinger equation of quantum mechanics. So that's why there's one painting left for you to figure out the final equations which is going to unify this. That's the quiz on the way out. But it's just remarkable how powerful these equations are and how much they can capture with so little. That's why I think of them as art. Some people like them so much they even put them on their tombstone, like I found when I went to visit Erwin Schrödinger's grave here. And it's not just patterns and shapes that are mathematical in nature, and it's not just the equations, it's even numbers themselves. For example, this is a list of 32 numbers in the rightmost column here. Not numbers even with units, just pure numbers. And remarkably, using just those numbers and the equations of physics, we can calculate in principle every other number that we have ever measured in the history of physics. Every single fundamental physical constant can be predicted. Hundreds of thousands of numbers, for example, giving properties of what kind of colors of light come out of different kind of atoms, can be calculated just from these guys. Every measurement made at CERN, at the Large Hadron Collider, can be calculated from those 32. It's pretty remarkable. So by 1960, which is actually before the Higgs boson and before this final list of numbers here, Eugene Wigner already thought that this is just too much. I mean, he said the enormous usefulness of mathematics in the natural sciences is something really bordering on the mysterious. And really called, there's no rational explanation for it. It kind of feels like there could be an explanation. So in this book, I explore the range of possibilities. I explore the possibility that it's just a fluke, which a lot of people think that there really is no explanation. And then there are a lot of people who think that there is something kind of mathematical about our universe that has some mathematical properties, but some properties that are not mathematical. But maybe it doesn't mean anything, or maybe it has something to do with the brain, or maybe we invented the math to match our universe. There's a fascinating range of opinions. And then I also explore the opposite extreme, which is the idea that I find the most exciting, which is that there really is a very deep explanation. Namely, that our universe isn't just described by math, but that it is math, and specifically that it's a mathematical structure. I'll talk a bit more about that. basically our world doesn't just have some mathematical properties, but it has only mathematical properties. So it's well known in mathematics that you can often approximate some complicated math by simpler math. And that means that what we might have been doing so far throughout the history of physics is finding more and more complicated math that approximated the true math better and better. Except we haven't quite found it yet, right? Because we haven't gotten quantum mechanics and Einstein's theory of gravity to get along with each other. But maybe one day one of you guys can find it. Now, before we go any farther with this, I'm glad they serve Fibonacci cocktails here, because it makes it a little bit easier to handle these really crazy sounding ideas. But we still have to ask ourselves, isn't this, just total hogwash? It sounds just too crazy. How can we say that the world is just totally mathematical? And to emphasize just how nutty it sounds, I want to introduce you to Mr. Huggles. Mr. Huggles is a groundhog. He is our neighbor. Actually, I shouldn't say that he's our tenant because he lives in our backyard. I think he thinks we are his tenants because he lived there first. If you look at him and you ask, what properties does he have? What comes to my mind is properties like cuteness, charm, herbivorousness, maybe an amazing fascination for digging, and great appetite for grass. Those do not strike me at all as mathematical properties. But yet, we know that Mr. Huggles, and in fact everything else in our world, is ultimately made of elementary particles, like electrons and quarks. And what are the properties of an electron? Well, as you can see in this table here, the electron has the properties such as -1, 1/2, and 1. And we humans have made up nerdy names for these properties, like electric charge and spin and lepton numbers. But the electron doesn't care. Those are just human words. The only properties the electron has are these mathematical properties, these numbers. So the electron is actually a purely mathematical object in the sense that it has no properties at all besides mathematical properties. And the same goes for all of the other building blocks of everything around us, all the other particles. Only mathematical properties, they're just different choices of numbers. So if everything in space has only mathematical properties, what about space itself? What properties does space have? Well, it has the property 3. That's the largest number of pencils you can put that are perpendicular to each other. We again have a nerdy name for it, we humans. We call it the dimensionality of space, the number of dimensions. But that's, again, space doesn't care. That's just a word we made up. The basic property it has is 3. It's a mathematical property. Einstein realized that our actual physical space is more interesting than the space of Euclid, which only has the property 3. It also has properties called curvature and topology. But if we have any math students in the audience or mathematicians, they will know that these two are purely mathematical properties that mathematicians study and write papers about. And as far as we can tell, space itself is a purely mathematical structure in that it has no properties at all except mathematical properties. So if you accept the idea that both space itself and all the stuff in space has no properties at all except mathematical properties, it starts to sound a little bit less insane, the idea that maybe everything actually is mathematical. Now, what does that mean? We've talked again about how we've underestimated not just the size of things, but our power to understand it, and how the reason that we can understand it so well has a lot to do with the fact that things are so mathematical, that we can, with a small number of observations, see all these patterns, and then generalize and use that to predict the future. So what does it mean for the future? What does it mean for the future of science, for example? Well, if this idea is wrong, and there are some properties of our world that cannot be described mathematically, it means that physics is ultimately doomed, because we're going to hit an unsurmountable roadblock. There will just be no more patterns to discover, and we're stuck. But if this idea is correct, if it's all mathematical, then that means that there is no roadblock. All the clues are in principle out there to be found, and there's nothing that we cannot in principle understand about our world, and our ability to actually figure stuff out is only going to be limited by our imagination, which I think would be awesome. For example, if consciousness, which is something I think we'll all agree that we don't particularly understand, and if it can be understood as particles moving around in beautifully complex patterns that process information in some intricate way, then that would mean that even I can be described mathematically. I think it's very important to not get your ego crushed by the fact that we are much smaller than stars and galaxies, because so just to cheer you up, reflect on the fact that of everything we've seen so far in our universe, the most complicated and beautifully intricate structure ever discovered is the human brain. It is so elaborate, the pattern of particles moving around in your minds, that it totally blows away something like the sun, which is just a boring blob. Yes, it's big, but it's really boring and really simple. So, in summary, our human minds really have the power not only to understand our world, but also to shape and improve it. So I want to conclude my remarks here this evening on this theme. I'm asking, okay, if we have the power to shape our world as well, what are we going to do about it? The cosmic perspective that I've shared with you, that things are so much bigger than we thought, means that we have much more potential in the future than we gave ourselves credit for, right? We don't just have the next election cycle or the next 100 years. We have billions of years at our disposal. And we have 10 to the 57 times more volume out there that we could in principle do cool stuff with. Maybe even make some of it come alive. What are we actually going to do? Well, as you know, literature is full of speculations for different options. Maybe we'll get our act together, and maybe life can even spread into our universe, and maybe much of our universe can come alive. There are all sorts of wonderful possibilities. Or maybe we'll just decide to log out, and terminate life through some accidental nuclear war. Maybe we'll invent some super intelligent machines without really thinking through the consequences, and that'll be the end of it. Maybe we'll mess up our planet in some other ways. There are a lot of options here, right? A lot of possibilities, which means that what we do here is actually very significant. In the last part of my book, I talk about bringing all of this cosmic perspective back home. What does it really mean for us? And I talk about the fact that if you take all of the risks that people tend to worry about the most, the really big risks that could wipe us out, you notice something really interesting, which is if you organize them by how far in the future they're most likely to wipe us out, you see that all of the most urgent risks that have the potential to wipe us out the soonest are actually risks which we cannot blame on the big bad universe out there, but we can only blame on ourselves. These are all risks created by the technology that we have invented and by the things that we are doing. So in other words, if we can get our act together and not wipe ourselves out, we have much more time to use our creativity to take on these various other risks. For example, if anyone later wants to ask me about how we can avoid getting destroyed by an asteroid impact, or how we can avoid the sun vaporizing the oceans in a billion years, I actually can tell you about some really cool technical solutions to both of those problems. And we'll have plenty of time to implement them if we can get past our midterm here and deal with this. Speaking of midterms, I confessed that one of the bad habits I have as a professor is I love giving quizzes. Another one is I just can't resist giving out grades left, right, and center. So I decided to give humanity a grade for Risk Management 101. Okay? So I asked some of my friends, and a lot of people thought I should give a B+, because there have been a lot of challenges, but hey, we're still here. Okay, there were some close calls, Cuban Missile Crisis, a few other thing, cases where maybe we played Russian roulette one time too many, but we're still here, you know, that's not so bad, right? So maybe a B+. But I actually gave a D-. And the reason for that, I don't know if we should applaud ourselves for D- performance. The reason for that is because I think we shouldn't think in the standard perspective, where we think of ourselves as the pinnacle of evolution and are just obsessed about 50 years in our planet. We should think big. We should think in the cosmic perspective. We have so much potential. We have billions of years, we have all this space, we have so much we can do. And in that context, I think it's actually pretty pathetic to keep rolling the dice like this and playing Russian roulette. You know, some people think the probability of us wiping out in any given decade is maybe only 1 in a million or 1 in 10,000. Some people think it's maybe 10% chance per decade. People have very different assessments. I think any of those kind of risks are totally unacceptable if you have so many decades ahead of us where we can do awesome stuff. We have so much potential. So why are we? Well, when I give a grade, some student will come back and complain and say, okay, can you justify this? Why did I get a D? And I should say also that, just so you understand how bad a grade this is coming from me, I'm actually known as being a very lenient grader at MIT. I'm just going to give you one very concrete example of why I'm giving you D-. It's because there are actually more people on this planet who have heard of Justin Bieber than who have heard of Vasily Arkhipov. Even though the one of these two men who single-handedly prevented a Soviet nuclear attack during the Cuban Missile Crisis was, surprise, surprise, not Justin Bieber. And I mean, come on, that's pretty screwed up. That's pretty seriously screwed up priorities. D-, I say. You should thank me for humanity for not giving an F there. I'm just giving a D- because the course isn't over yet. There's still room for improvement, okay? So why are we being so short-sighted? Why are we being such lousy stewards of our planet? Why are we taking all these risks? Well, the first answer I usually get is we just cannot afford to invest a lot of resources in mitigating these risks because we just don't have the money. Well, I'm a science nerd. If someone says we don't have enough money, I say let's look at the numbers. There are some organizations who are actually doing some wonderful work to try to reduce some of these risks, like accidental nuclear war, for example. Probably the best funded one is the Union of Concerned Scientists. I talk about all this in the end of the book. And they have a budget of about $20 million per year, mostly from private donations from people like you. So 20 million sounds like a lot of money, but let's shrink it down so 20 million corresponds to this little area of pixel here, covered by my finger, okay? And let's compare that with some of the other very urgent things we spend money on. This is what we spent on plastic surgery last year. 10 billion. This is what we spent on air conditioning for US troops alone last year. 20 billion, okay? This is what we spent last year on smoking in the US alone, okay? And don't get me wrong, I'm a big fan of personal freedom. If you want to go light up, you know, fine by me, you know, but if someone comes and says to me, you know, we just can't afford doubling the amount of money we spend on worrying about the future because that would just take, you know, the cigarette prices would go up by, you know, some puny fraction of a thousandth of a percent, you know, and that would just be devastating. If that's the kind of reason a student gives me to why I should raise their grade, sorry. And I haven't even shown you the biggest budget item. It didn't fit. That's because it didn't fit on my slide. So I'll have to shrink everything for this to fit. How much we spend on military. And is this really so unimportant? That's for you to choose. But so this clearly can't be the real reason we're spending so little effort on safeguarding future generations. But there is another reason I'm often told as well, which is very interesting. I'm often told that it would just be irresponsible for us to devote a lot of resources to mitigating risks that aren't proven. You hear this a lot in the news, and to to see the logical flaw in this argument, I want you to imagine for a moment that you're in a store buying a stroller for the baby of a very close friend of yours. And the smooth salesman comes up and says, hey, I have this awesome stroller here for $49.99. It's a very robust model. We've been selling it for over 10 years. There have been no reports ever of any safety issues or malfunctions with it. $49.99. But then I have this stroller. It's only $39.99. And yeah, I know there have been some reports in the press about it sometimes collapsing and crushing the child and stuff. But you know, frankly, the evidence has never been really well substantiated, and there hasn't been a single case where anyone has been able to really prove in court that those deaths were actually caused by any manufacturing flaw in the baby carriage. And hey, it's 20% cheaper. So wouldn't it be irresponsible of you to spend 20% extra just to mitigate a risk that hasn't been proven? Well, if you're willing to spend an extra 20% to mitigate the risk of killing a child, one child, then of course, if we feel that it's irresponsible if we feel it's not irresponsible to spend money on risks that aren't proven, then you would feel that it's irresponsible instead to not spend money on risks unless we can prove that they're not dangerous, right? And if you're willing to make that argument to save the life of one child, surely you would be willing to make it also when the life of every child on the planet is at stake, because that's what we're talking about here, right? Not to mention the life of all the children that haven't been born yet. Not just the next generation and the next generation, but all generations that might exist on our planet and maybe even elsewhere for millions or billions of years. So in summary, when we think about the various options we have here for the future of life, I want to emphasize, first of all, the potential is much, much better than we used to think before we realized just how much time and how much space we have at our disposal. Second, our ability as humans to understand nature and actually shape it for the better is also much, much grander than we thought. So although we're small, we humans have a great power to understand and improve the world around us. Let's make a difference.